All right. Good morning, everyone, for another lecture. Welcome to another lecture in numerical methods. This is our next chapter. Now it's going to be on numerical integration. We'll try to finish up today. It's a fairly short and simple lecture. The next couple of chapters are fairly easy, and then difficulty is going to start climbing again. So I hope you'll enjoy those. I'm going to start by showing you a plot of the metric CO2 emissions per capita. So these are in metric tons on the y-axis, what you're seeing. So 3 metric tons per capita over the years. So starting from about 1960 all the way to 2016. And so you see this fluctuation in the metric tons of CO2 emissions over the years. That's just data that was presented to you. And as we learned in this class, first thing you do is plot the data. Now, my question to you is, and the first activity is, how do you estimate the total emissions of CO2 from 1960 to 2016 per capita? Okay, so I want you to take a moment, just given this plot, you might have access to, assume you have access to the data, the table itself, to the original data, so like XY data, but also visually, you know, how would you estimate the total emissions given those data? All right, I'll see you on the discussion. All right, I am over here, and I'm gonna try to spin up the wheel. Okay, wheel of names. That is going to show up a second now. All right, got the wheel of names. Let me resize it so that the YouTube stream will be okay. Sometimes these ads start popping up and you get like, I get like suggestions for dinosaurs and whatever. It's because I'm always shopping for dinos for my kid. And so yesterday he wanted a quadrupus. Now he wants a quadrupus. Since if you remember the septupus story, I was teaching him about you know, quadro and penta and hexa, etc. And now he wants a quadrupus. So I grabbed the paper and I cut it with scissors. Couldn't find a quadrupus. Anyway, so if you see one of those ads showing up over here on the wheel of names, that's because in my downtime I'm shopping for non-existing animals. All right, so let's see. Do you have any ideas on how we could do this? I'm going to share my screen on Zoom because we might need to draw a couple of things. Okay, let me see. All right, so any thoughts? Any volunteers? Just give me ideas. How would you calculate the total emissions? Sammy, go ahead. You don't need to multiply by the year, right? You can just add them all up, right? Because yeah, that the year it's just really doesn't matter because these are kind of by unit, right? But I know what you're after. What would be another idea if you didn't have access to the tabulated data? What if you just had this plot and you had, you know, you had a value over here and a couple of other values? Let me annotate. Okay, let me use the, okay. So let's say you had this value over here and that value over there. How, just geometrically, how would you do this? Abby? You don't have the data. Let's say that's yes, that is, if you had the data, yes. So you're saying like do a fit and then integrate the fit. Yes, yes, absolutely valid. Yep. What other ideas do you have? Come on. Uh-huh. Okay, like this. And then, yeah, just calculate the area of that triangle, right? The area over here. Okay, great. How could you make it better? So that's what Sami suggested. What about geometrically? I want just kind of geometrically, what would you do? I could draw, how about drawing a line over here and calculating the area of this triangle, and then a line over there and calculating the area of this triangle, the line over here and calculating the area of this trapezoid, and another line over here, trapezoid, and you know, something like this, right? Kind of geometrically, right? And then can compute all of those areas, right? Wouldn't that work? Yeah, that is a totally legitimate way of doing it. In fact, this is the basis of numerical integration. Okay, and this is the basis of what we call quadrature. It's essentially taking a complex set of data or a complex function that looks some funky weird shape and dividing it into small quadrilateral elements. Okay, and that's where the word of quadrature comes from. Right now, you could improve this by saying, okay, I'm gonna take every 2 points and I'm gonna, you know, draw a quadrilateral or like a trapezoid or something, or do a local fit like Abby was suggesting. Instead of doing the entire fit over the entire data set, you could take every 3 points, for example, and do a fit and integrate, and then etc. do a fit and integrate, or every 4 points or every 2 points. All of those are possible options that we're going to discuss, but they each have advantages and disadvantages. All right. Good discussion. I will see you on the other side. All right. So you guessed it. We could draw a line geometrically, a bunch of lines. We could add the points. All of those options, they're all valid. Right now, for numerical integration, we have a set of objectives that we would like to accomplish at the end of this chapter. And numerical integration is going to apply to both continuous functions, like you're given integrate sine x squared, sine squared of x, you know, times e to the minus x squared, some complex functions like that, all the way to discrete data that are given to you, like the CO2 example we just discussed. At the end of this chapter, my goals is that you will be able to define what quadrature and numerical integration means. They're the same thing, and we just kind of defined quadrature as essentially taking a complex shape and dividing the area under it into small quadrilateral elements and adding all of those up together to compute the area under the curve. Calculate the area under an analytical function using what we call Newton-Cotes formula. So this is the basis of what Abby was suggesting. It's called Newton-Cotes formulas. Calculate the area under a discrete set of data points, also using Newton-Cotes formulas. Use the left, right, midpoint, trapezoidal, Simpson's 1/3, and Simpson's 3/8 rule to calculate the integral of a function or a discrete set of points. So those are the methods that we will learn in class today. Determine which integration formulas apply to equally spaced data and which apply to unequally spaced data. So data could be presented to you in different manners. You could have equally spaced data like the CO2 data every year, but then what if you had data that was given to you every year, and then every 3 years, and then every year and a half, and then every 3.5 months, you know, very complex, like very unequally spaced. So what do you do in that case? And then get an idea of what the error bounds are for all of the methods that we will discuss. The idea of numerical integration is simply find the area under the curve given a function f of x, whatever that function is, shown here in this red curve. Find the area under the curve between 2 points, a and b. Okay, and that's the definition of what you learned as the integral. That's the geometric interpretation. It gives you the area under the curve. The first method of doing these integrals, calculating these integrals, we're going to first talk about continuous functions, but then we'll extend what we learned to discrete data. The first set of, or what we will learn in class are Newton-Cotes integration formulas. Those are really easy, and they are based on what we already covered in class using interpolation. All right, and the idea is to approximate the function locally as a polynomial. So the 2 points a and b, where you were trying to integrate f of x, you want to fit a polynomial into those data, just like Abby suggested. The first set of, so clearly you could do a first order, second order, third order, nth order, whatever order you want, right? Now we know the advantages and disadvantages of high order polynomials and being oscillatory, etc. So first we're going to start with the simplest polynomial, which we are going to call left, right, and midpoint rules. And the idea here is that you approximate f of x as a constant. That's a 0th order polynomial. That's the simplest polynomial you could derive. Now, you could choose this constant in a number of ways, but if you set f of x equal a constant over the interval a and b, that's clearly, you could say that's a horrible approximation. I'm going to show you in a second how we can make that a really good approximation. Then you put c into the integral. That's a constant, right? Integral from a to b of f of x dx, that's approximated as c dx, then that gets you cx, so you get simply b minus a times that constant. Now, clearly, you could choose that constant in different ways, not clearly, but as will become apparent in a couple of slides. If you are taking, again, this function and the integral from a to b, one of the choices is to choose that constant to be equal to the value of f at a. So you take that value as your constant. Now, if c is equal to f of a, then you've approximated the entire function as this constant over here, right? As f of a. So then you're evaluating the area under the curve, you're approximating the area under the curve by this rectangle. And then simply that's what you get, b minus a, that's one of the sides, times f of a. That's called the left point rule, because you chose your constant, you approximated the function as the value at the left point, okay, f of a. Now you could do the same and say, instead of f of a, I'm going to take f of b, okay? Same thing applies. That would be your constant, and you approximate the function with that value over the entire interval. So you approximate your area under the curve by this rectangle, and then the calculation would be b minus a times f of b. All right. Now we can do better. Okay. What if we take, clearly when we did f of a, we underestimated the area. When we did f of b, we overestimated the area in this case because of the shape of the function. Now, what if you take some point in the middle, like the midpoint, a plus b over 2, and you say, my function is this value. We're going to approximate it by this value. Then you draw this rectangle, and then your area would be b minus a times f of a plus b over 2. Okay. Now, in this case, you overestimated the integral here, and you underestimated it over there. So you're hoping that you might, you're doing something, you might be compensating for any issues you create. Okay. Now, there's a problem with the midpoint rule in that if you have discrete data that is not equally spaced, you cannot define a midpoint discretely, okay? Because if you think about it, discrete data is given to you as f of a, f of b, f of c. If they are equally spaced, then you take the point in the middle as the midpoint and you calculate the area, but you're losing one every other point, okay? Now, for unequally spaced data, that is going to be problematic for sure, okay? So let's go ahead and do an activity, a coding activity. Before we do that, we want to be able to compare our routines to something built-in in Python. Now, as you proceed in your career, you'll just use built-in Python routines. But there is some wisdom behind the madness of us implementing our own routines, is to train you to think programmatically and to train you to think about how approximations work. So when you do it by hand a couple of times, you're like, yeah, I know how this works. And then from here onwards, I'll use built-in routines. For continuous functions, you can use a routine from SciPy called integrate quad. Quad stands for quadrature. And it's a very simple routine. You give it the name of a Python function. So you would define your function, sine squared x or whatever function that is, and you give it the bounds a and b, and it will do the quadrature for you. It uses some really advanced quadrature methods. So we're going to treat this as the truth, as the true value. Still not the exact value, but it is as good as it gets. So we're going to compare whatever we implement to integrate .quad for continuous functions. And this is a summary of the three formulas. And now I'm going to ask you to download a Jupyter notebook called Quadrature with Gaps from Canvas. You can find it under the module Numerical Integration or under Files, Jupyter Notebooks, Quadrature Activities. Download that notebook and download with it. There's a CO2 data. We're going to need that in a few slides. So go ahead and download that data file as well. And your objective with this first coding activity is to just develop 3 Python routines that implement the left point, right point, and midpoint rules, okay, for an arbitrary function. So your routine should take at least a function name and lower bound and upper bound. So it should take at least 3 arguments. And then I want you to apply it to calculate the integral from 0 to 1 of this complex function. 1 was 0.5 sine squared, 1.75 pi x dx. All right, I will see you on Zoom. All right, everyone, I am going to share my screen on Zoom. And let me see, desktop 3. Okay. So now you can follow me on Zoom. This will still be recorded on YouTube. Unfortunately, I'm having difficulties getting the audio, your audio, through my mixing software into YouTube. So you will not be heard on the YouTube when you replay, but I will try to repeat my question. My audio is still being recorded, but for some reason, your audio is not. So I apologize about that. All right, so go ahead and download that notebook. I'm assuming most of you got that. Still working on it. All right. Anyone still working on it? Okay, I assume that you got it. All right, so first of all, just standard boilerplate, but notice over here, I'm also importing from SciPy import integrate, okay? Because we're gonna need that. And the first activity is to integrate this function, f of x is 1 plus 0.5 sine squared 1.75 pi x, okay? And so first I wanna define this function and plot it, just to see what we're dealing with. And simply, to define this function, you just create a standard function routine. I'm gonna call it my function, my f, and it takes one argument, x, and it returns 1 plus 0.5 numpy sine 1.75 numpy pi times x all squared, okay? Then I create a linspace and just plot that. And our goal is to evaluate this gray area under the blue curve. Okay, so that's the blue curve. If you want to know how I created this gray area, look at this fill between. Okay, that's beyond what we're doing here. But anyway, this is what we're after. Okay, now I am asking you to define 3 routines, left rule, right rule, and midpoint rule, that take these three arguments, a function name, f, and an A and a B for the bounds. Now remember that it's hard to see the slide over here. Let me try to bring in the slide into the shared window as well. Okay, so these are the formulas for the left point rule, the right point rule, and the midpoint rule. All right, so go ahead and just fill in the return values. Remember, the left rule uses the lower bound. The right point rule uses the upper bound to approximate the function over the interval on A, B. Okay, and the midpoint uses a point in between. All right, any takers? Yeah, go ahead. Okay, so does that work for an arbitrary function? This works only for this integral. So if you were to use Python as a calculator, I agree with you. You would do 1 minus 0 times my f at 0. Okay, that's the integral that you would get. I agree with that. But what if I change my function? What if I change the bounds? You're using Python as a calculator right now. I want to define a general routine that implements the left rule and right rule and midpoint rule. All right, let's see. William? Yeah. Uh-huh. Again, why my F? What if I, yes, exactly, times F of what? At A, correct. Now remember, this left rule takes three arguments. It takes the name of a function that I want to integrate and integrates it over the interval AB. All right, give me the right rule now, someone else. Mm-hmm. F of B, all right. And the midpoint rule. Mm-hmm. Okay, good. A plus B over 2. All right, I want you to think programmatically. What your colleague said initially, that's not wrong. If you're using Python as a calculator, you're testing things out. But to generalize, to make a routine useful, you have to allow it to be generic. Okay, so now we can simply apply. So let me show you. We can simply apply any one of those rules to our function. I could just do left rule. Okay, left rule into my f 0, 1. And that gives me the value 1. If I want to do right rule, I can do the right rule, my f 0, 1. That's going to give me 1.25. And if I want to do midpoint rule, my f 0, 1, you get 1.07. So that's clearly three different answers. And it is actually a horrible approximation, but let's see how bad it is. We're going to compare this to scipy.integrate. So I'm going to type in integrate dot quad for quadrature. And quadrature takes a bunch of arguments. I'm only interested in the first three, my f 0, 1. And that gives you 1.272, with this error, 10 to the minus 12. But that's what this gives you, okay? So we're like hovering somewhere close. In this case, the right rule was closer to what we're going to assume to be the true value, okay, which is what integrate.quad gives you, okay? It's very simple, really straightforward. Now, we have committed a really bad error over here because we took the entire interval and applied, just took one value for the entire interval, okay? Next, I'm going to discuss how we're going to improve this, all right? And I will see you on the stream again, okay? All right. Next, we're going to see how we're going to improve our guess. So as you just saw, we're clearly committing some really bad some really bad errors over there, okay, using the left mid and midpoint, left point, and right point rule. Those rules are not bad themselves, but the problem is the length of the interval, how big the interval is, okay? So what if we say, okay, rather than apply those rules to the entire interval, however small or big it is, why don't we subdivide that interval into smaller segments and apply that rule, any one of those rules, the left point, right point, or midpoint rules, to those segments? Wouldn't that increase accuracy? Absolutely. That's, in fact, what I was doing when I looked at the CO2 data and I started drawing small trapezoids or quadrilateral elements under all of those points. So pictorially, this is what this would look like. Rather than just taking one value for the entire interval AB, we're still going to integrate from A to B, but we're going to artificially subdivide our interval into smaller segments, into little segments, and then apply whichever one of those rules, midpoint, left point, right point, to each one of those intervals. So in other words, for the midpoint, what this would look like would be x2 minus x1, where x2 is the first point, x1 is the second point, and x1 would be the first point, A, times, f of A plus B, f of x1 plus x2 over 2. And then we do the same thing for the second interval, for the third interval, and so on and so forth. Okay, so you get this kind of lengthy formula. Is just simply a repetition of the midpoint, left point, or right point rules at any one of those segments. It's really conceptually not that difficult. Now, programmatically, to do that, you're going to have to do a couple of tricks to do this. And the idea would be to create a linear space, an artificial linear space between the bounds, and divide those bounds into however many segments you are interested in. Clearly, the more segments, the more accurate, but you're going to reach a point where adding more segments is going to be insignificant, okay? And you can study the error. We will look at the error bounds at some point, but you can look at how well your approximation is converging. But the idea is simple. Again, we're going to take that interval, A to B, we're going to divide it into a number of segments, and we're going to apply any one of those rules, left, mid, and right point rules, to each one of those segments. We're going to add up the little areas, the areas created by these segments, and that would be our integral, okay? So now our coding activity, second coding activity, is to do just that. We're going to develop a Python code that computes the integral, again, for an arbitrary function. We're not talking about discrete data yet, and with an arbitrary number of segments. In other words, your routine needs to take a function, needs to take a lower bound, an upper bound, and a number of segments, because that is going to allow us to control the accuracy, okay? And we want to apply those routines to calculate 1 plus 0.5 sine squared. And we'll play around with that a little bit to see how close we can get to SciPy, to integrate quadrature, okay? Switch back to your Jupyter notebook and try to take a stab at any one of those rules. What I've given you here is most of the work that needs to be done. I put some question marks. Pick one of the rules and just implement what we just discussed into the code. So just to give you to explain to you what I did here, let's look at the left rule. What I defined this routine as, it takes 4 arguments, the function name, because I want to apply it to an arbitrary function. It takes a lower bound, an upper bound, and a number of segments, okay? Now, first thing I want to do is create those segments, because the abscissa in those segments, because I need to know that distance, b minus a, okay? I need to know that distance, and I need to evaluate the function at each one of those abscisses, right? So the way I do this, we do it with linspace. Okay, we're going to do this with linspace. Linspace is going to go from some value to some value and however many segments n. Okay, now you can linspace, remember, gives you points or segments. You gotta be clear in what you mean by n. Okay, so if you mean by n as the number of segments, then linspace needs to be n plus 1, because that gives you points. Okay, so I'll give you that answer over there. Then we declare a variable called result, which is going to store my integration. Okay, result. That's where that integral is going to show up. And then I'm going to loop over each one of those segments. Okay, I'm going to loop over each one of those segments, and we're going to start filling in A and B, and then integrating using the left rule, applying the left rule, right rule, or the midpoint rule. Okay, so go ahead, take a few minutes and apply it over there. Let me see, what did I do here? Sorry. Just pick one of those rules and try to fill in the blanks. Try to figure this out. If you're confused about linspace, just do a, just test it out. If you do np.linspace, let's say from 0 to 1, and you give it a number 3, that is going to give you 3 points. Okay, so in other words, 2 segments. Okay, so this needs to be, if you want n segments, linspace needs to have n plus 1 points. Okay, I want you to think in terms of segments, because each segment has 2 points. All right. And then you're going to loop over the segments. How many segments do you have? Then you treat each segment. First segment, you want the lower bound and upper bound, and then you do the integration. And then the second segment, lower bound and upper bound, and so on. All right, let's see. Do we have any takers? All right, let me see. Okay, Porter, go ahead. Correct. Yes, I agree. Okay, hold on. A to B with n plus 1 points. Because n plus 1 points is going to give you n segments. And we're thinking in terms of segments, right? Okay. All right. Now, well, are you sure? Okay, so let's see what range does. Should it be from 0 to n or from 1 to n? From 1 to n? Okay, let's see 0 to n, and let's see if it's going to work. Okay. And okay, so what did you do here? A would be xi, clearly, right? I plus 1. And then for result, okay, f of a times b minus a. That's the left rule, correct? Okay, so I'm going to take this, put it up here so that I can evaluate it. Okay, and let's try. Let's try it. So let's do left rule. Oops. Let's do left rule of my f, correct? Going from 0 to 1. Let's say what, 20 segments? You run it, you get 1.2659. Okay, let's compare that to integrate.quad. What was it? My f 0, 1. Okay, and that was 1.272, right? So we're getting close. What about, 50 points? We keep getting close, right? 50 segments, sorry. 60 segments, 1.27, say 100 segments, 1.271, we keep getting close, and then 600 segments, 2725, and then it's just going to start converging very slowly, okay? So you got it, that's right. Okay, who wants to do the right rule? So a point on this range, if you're confused about the range, okay, again, print it out. So for I in range 0 to n, print I, okay, print I. So if we're doing range from 0 to 10, that is going to give you an index 0 to 9, okay, which is correct because our linspace starts at x0, okay, to xn, okay? Fact, all right. Left rule, okay, let's delete this. Okay, who wants to do the right rule? Again, A, B, and n plus 1 segments, correct? That is correct. Yep. So we're going to go from 0 to n. Should we go to n plus 1? So it just occurred to me that we might have made a mistake. So how would I debug this? Should we go to n or to n plus 1? Okay, what is the indexing going to tell us? So if we were to create a linspace from 0 to 1 with like 5 points, and you print that, oops, np.linspace, you print that, you're going to get 1, 2, 3, 4, 5 total points, right? You're going to get 5 total points. In other words, this value over here, okay, this value is going to, if this value, you call this value n plus 1, this would be n, okay, because x0, x1, x2, x3, and x4, right? So it's this value minus 1. So I think what we have is correct over here because we need to have an xi plus 1 over here for the upper bound. Otherwise, we are going to go out of bounds. So Abby, you said here it's b minus a times f of b. And same thing over here. The linspace going from a to b, and we need n plus 1 points. And the range is going to go from 0 to n. Okay. And then b is xi plus 1, I plus 1. Now for the midpoint rule is b minus a times f of a plus b over 2. Okay? A plus b over 2. And then you execute this. So let's try this again. Left rule, right rule, midpoint rule. Yeah, look at that. The midpoint rule is probably going to be more accurate than the other ones. Because the midpoint just gives you an average between the left and the right. Okay, so the midpoint rule in this case is a little bit more accurate, but we'll see the error bounds at the end of the lecture. But this is how you would apply this for a continuous function. Okay, we might have an index missing over here. You know what? It's not going to matter because as you increase the number of segments, you're going to get as accurate as possible, okay? I suspect we might have a little bug over here. I'll dig through it after the lecture, but this is how you would do this, okay? And I have the code for, you can use these codes in your homework. You can compare with quad. Now, in reality, in practice, you're just going to be using quad. But this illustrates, this is no different than what quad is doing, okay? Yeah, go ahead. I don't understand the question. So for each segment, I'm defining an A and B value. Okay, so I'm treating each segment is the same way we kind of defined our integration. You're integrating that function over that segment from A to B. So I define A as my lower bound of the segment and B as my upper bound. So that's why, yeah, does that, okay, great. So yeah, so B is just going to be the next point in the segment, okay? The upper bound of the segment. All right. All right. What about discrete data? Now we did this for a continuous function, and the great thing about a continuous function is that you can just simply take that function f and apply it at a, evaluate f of a, f of b, f of a plus b over 2, f of a plus b over 3, whatever you want, okay, in any given segment. That's the beauty of having a continuous function. But what about discrete data? Okay, and assume you're given data like this, okay? The left point rule, it readily applies. Whether the data is equally spaced or not, it doesn't matter. You just go over your data, over each segment, pick the left point, because there's always going to be a left point, and you just evaluate your integration. You take f of, the left point value multiplied by the size of the interval of your data, whether they're equally spaced or not, and then add it up, and so on and so forth. The right point rule, also the same thing, because for every segment, whether the discrete data is equally spaced or not, for each segment, you always have a right point, correct? And then you just simply take the value of that right point and multiply it by the spacing between the 2 points, and you just add them up. Now, for equally spaced data, the spacing is a constant. You can just keep reusing that to calculate the area. For unequally spaced data, unfortunately, you're going to have to look at the x values and make sure you take the difference between xi plus 1 and xi to calculate the segment width. All right. So now my question to you is, what about the midpoint rule? Does it apply to discrete data? And under what conditions? I alluded to that a little bit earlier, but I'm going to ask you now to think about it and try to give me an answer. Okay? All right. So my question to you was, does the midpoint rule, we saw that for discrete data, the left point, right point rules apply readily, because for any segment in discrete data, whether the data is equally spaced or not, you can always find a left point and a right point. What about the midpoint rule? Okay, I'm gonna spin. Tess, are you with us? Tess is usually with us. Why is not here today? Let's see someone else. Emily. Emily. Okay, I'll do one more spin. Yes, Emily. Yes, yeah. This Emily. All right. Do you have a thought on the midpoint rule on discrete data? Remember, the midpoint rule takes assumes that the function is equal to a constant, and that constant is equal to the midpoint value of the function on the interval. So for discrete data, do you think we can apply the midpoint rule? You do not think so? Why not? So think about the midpoint. Where would that midpoint be? How would you define the midpoint? For a continuous function, you can evaluate the function at any point, a plus b over 2, whatever, right? But for discrete data, you need to have, what is your midpoint? You need to have the midpoint of the interval. Yeah, but that doesn't give you any new information. You might mess up the interpolation, right? I mean, you could do a straight line and do an evaluation, and that's a legitimate answer. That's completely legitimate. But what if you're not doing any interpolation? How would you define the midpoint? I saw Sydney was nodding her head. So do you want to jump in, Sydney? Okay. Okay, that's right. So can you elaborate on that? If the data is equally spaced, then you would take every other point, right? So your segments will be bigger, but they need to contain that point in the middle, right? What about unequally spaced data? Can you do that? No, you cannot apply the midpoint rule. That's right. You cannot apply the midpoint rule. Now, you can take every other point, but it would be some other rule. It would be like, what if the point in between was 1/3 of the way, or like 5/6 of the way, right? And so it would be a different rule, which is again also kind of possibly doable, but it's not the midpoint rule. All right. Good discussion. I'll see you on YouTube. All right. So the midpoint rule, like Sydney and Emily said, is problematic for discrete data, can be problematic for discrete data because we cannot always define a point in the middle. If the data is equally spaced, then you take every other point and treat that as your midpoint. So as in this example, if the data is equally spaced, then your interval, rather than being x1 to x2, it has to be x1 to x3, so that x2 is your midpoint value. Okay, so you skip every other point. However, for unequally spaced data, that is not the case. Now you can skip every other point, it's just going to give you some other rule, but it's not the midpoint rule. So I would not recommend you do that. Okay, now we're going to apply, so just to remind you where we're at. We started with continuous function. We defined left point, right point, and midpoint rules. We applied that to the entire interval, and then we subdivided the interval into segments, and then applied each one of those rules to each segment, and then added up the results. Next, we're going to apply this left rule and right rule to discrete data. Why did I choose the left rule and the right rule, didn't ask you to do the midpoint rule? Because they're just easier. The midpoint rule, you're going to have to reason about how many points you have. Do you have an even number of points, an odd number of points? You're going to skip the midpoint. I would just do the left rule and right rule. They are easily implementable. Okay, but we still need a mechanism to compare our discrete data integration, our own routines, to something else to verify our result. There is a function, one of the built-in routines in Python comes from NumPy, and it's called trapz. It stands for Trapezoidal Rule, which we will learn in the next few slides. But I recommend that you use trapz. It just takes y and x data and does an integration, discrete integration for you. And I recommend you use that to compare your results to. Okay, so go back to your Jupyter notebook now, and we are going to implement routines that use the left rule and the right rule to develop Python code to integrate discrete data. Now, your routine is going to have to take at least X data and Y data. And then internally, it's going to go through those data and just evaluate the integral. Okay? I'll see you in a second. Okay. Next, I declare a variable called result, and I initialize it to 0. That is going to be the result of my integral. Then I know that I'm going to need the size of the data. Why? Because I'm going to loop over the segments that the data was given to me as. Okay, and I'm assuming here, I'm making no assumptions here whether the data is equally spaced or not. Why? Because the left rule and the right rules, they don't care whether the data is equally spaced or not. Okay, but I need the length of the data, how many x values I have, so that I can define my segments. Okay, so if you have 5x values, you have 4 segments. If you have 50x values, you have 49 segments. Okay, if you have n x values, you have n minus 1 segments. All right, next we're gonna loop over the segments and then define a, b, define f of a or f of b, and then start adding up the values. So take a minute to fill in the blanks. The most crucial point is the range. What is going to be your range? How are you going to index your range? Okay. So remember, range is open at the end, okay? So if you go range from 0 to 5, it's going to give you 0, 1, 2, 3, 4. So think of the indexing. Your X array starts from x0, x1, all the way to xn minus 1. It has n elements in it as we define them here. N is the length of x, but x goes, and y as well, they go from x0, x1, all the way to x of n minus 1. That's the indexing, okay? So make sure your range is correct. You got to take into consideration that you're augmenting your range by +1 over here, augmenting your index by +1. So when you get to the end of the range, you want to make sure that you don't jump out of bounds, okay? So let's see. Do we have any takers for either one of those rules? Okay, yes. Thank you, Carl. Do you want to elaborate just a little bit on that? Why n minus 1? That's right. So we're looping over the segments. That's correct. And for each segment, we're going to take the lower bound and the upper bound. That's a great way to think about it. Okay. And so now what is A? Now, once you enter the loop, you are in the ith segment. Okay. You are in the ith segment. So what would be A for segment I? It's the same thing as we did before. And B? So A is the lower bound of that segment, B is the upper bound. Now, for the left rule, we want f of A, correct? So what would be f of A in this case? Correct. Yep, y on at the of the lower bound. And then simply you augment the result by the area of that segment, B minus A times f of A. Okay, let's do the right point rule. Again, we're gonna loop over the segments from 0 to n minus 1. Okay, and What about A? Same thing, is xi. B is xi plus 1. What about f of b? Yes, correct. It's the value of the function. That's the right rule. So we want to take the value of the function on the upper bound. The upper bound is I plus 1. Okay? Then you do this. And then simply left rule, right rule, you apply it to the data that was given to us here in the CO2 emissions, xi, yi. And now let's compare that to the trapezoidal rule from Python, mp.trapz. And trapz takes y values and then x values. So I'm going to give it yi, xi. Trapz gives us 232.88 million tons from 1960 to 2016. All right. So we're almost there with our left point and right point rules. Okay. So that's a pretty good approximation. Okay. All right. Let's now switch back and talk about more accurate methods. I will see you on YouTube. All right. Now that we've talked about the simplest Newton quotes formulas, just approximating a function by a constant, and look how far that took us, doing continuous functions with many subintervals and doing discrete data, left point, right point were the easiest because you don't have to worry about the spacing. Now it's time to talk about more accurate methods. And as you might have imagined, rather than approximating a function by a constant, we could approximate it by higher order polynomials. The first thing that comes to mind after a zeroth order polynomial is a first order polynomial. And in that case, we approximate the function f of x on the interval, the full interval a and b, as a straight line. So you take the value at A, the value at B, you draw a line, and then you approximate the area under the curve by the area of this trapezoid. And this gives you the trapezoidal rule. Okay, we're going to skip this activity, but by inspection, the area under the curve is simply the area of this trapezoid, which you learned how to do in geometry, and it's simply the difference between the two bases, b minus a over 2, and multiplied by the height, or average height times b minus a, and that gives you the area under the curve using the trapezoidal rule. You have a and you have b, and you just simply apply this formula. It's a pretty neat formula because it gives you a better approximation without any new knowledge needed in between the points. And the great thing is that this formula also applies to discrete data because you don't need any point in between. So it's going to give you a much better accuracy than the left point and the right point rules. Okay. So now I'm going to ask you a challenge question, an activity question. Calculate the true error integrating this function 2x plus 3 from 0 to 2. Okay, so calculate this integral, approximate it using the trapezoidal rule. Okay, now do this. If you can do this without doing any calculations, this is the formula for the trapezoidal rule. You can do the formula calculated by hand. But it would be better if you give me an answer without doing this, without applying the formula. What is the error in using the trapezoidal rule to approximate the integral of 2x plus 3 from 0 to 2? All right, I'll see you on Zoom. It's a trick question. Critical thinking. What did we do in the trapezoidal rule? What did we approximate the function as? All right, let me see. We're gonna spin the wheel. Oh, we got Abby. Abby, you already answered many questions, so no more for you. Sammy, you already answered more questions. Okay, no more for you. Okay, Harris. So look on your YouTube, calculate the error. Yeah, what is the error in using the trapezoidal rule to approximate the function 2x plus 3 on the interval 0, 2? All right. Okay. Let's see. Someone else? We got Porter. You already answered. All right. Adriana, you haven't answered today. Let's see. Do you have any thoughts? Yeah, exactly. Because the trapezoidal rule approximates a function as a straight line. So if the function is already a straight line, then you're gonna nail that. So the true error is gonna be 0 without doing any calculation. Okay, good call. All right. So like Adriana said, because the trapezoidal rule approximates a function by a straight line, if therefore, by definition, if the function is a straight line, then the trapezoidal rule is going to be exact for that function. And therefore, the true error is 0. Don't even have to do any calculation. The true error in approximating a straight line using the trapezoidal rule is 0. Okay. Now, what is the error in integrating a constant on the interval a and ab using the trapezoidal rule? This would have been an activity, but I'll give you the answer right here. It is also 0 because a constant function is by definition a straight line. Okay, it's by definition a straight line with a 0 slope. Really, it's just a straight line. So the trapezoidal rule is also going to be exact for a constant function. Okay. Now, there are other rules based on this. The next step, so we did a constant, we approximated the function as a constant, then we approximated it as a straight line. Next, we're going to approximate it by a second order polynomial or a quadratic. So we need 3 points in this case. So that's where these rules become more problematic for discrete data. But for continuous data, because you can evaluate the function for a continuous function, because you can evaluate the function at any point in the interval, then these rules are really easy to use and apply. But the idea here is you approximate the function on the interval using a quadratic. For a quadratic, you need 3 points. Remember interpolation, we needed, you had 3 unknowns. So you need 3 points. And once you do this, you do the interpolant just like we did before. We apply an interpolation. We take a point in the middle. And then this is the formula that you would get for the integral. Now, the critical thing here is that these points are equally spaced. Okay, the A point, the B point, and the midpoint in the middle, they're going to be equally spaced. And they're defined by this delta x, which is B minus A over 2. And so this is what you're going to get. Okay, for the Simpson's 1/3 rule, that's the rule. And now I ask you, what is the error in integrating y equal ax squared, alpha x squared plus beta x plus gamma on the interval, on any interval a, b, using Simpson's 1/3 rule? As you might have guessed, the error will be 0 because the Simpson's 1/3 rule uses a quadratic to approximate a function. And by definition, if you're getting a quadratic, you're approximating it by a quadratic. By definition, that's going to be exact for a quadratic. Okay. Now, taking this one notch up, you could do a cubic. Okay, that's the same thing. However, these points are going to be equally spaced. Okay, and the segment size is going to be b minus a over 3. So you repeat the same thing, and then you get this more complex formula. We claim this formula is going to be more accurate. And this formula, 3/8 rule, requires 4 equally spaced points on the interval AB. And again, if you're integrating a cubic using Simpson's 3/8 rule, It is going to be exact. I'm sorry, I'm rushing this a little bit because it becomes just repetitive. It's just a matter of applying these formulas. But the punchline is going to be where and when do you apply these where and when these formulas are going to be useful when you are dealing with discrete data. Okay, this is a summary slide of all of those rules: the midpoint rule, trapezoidal rule, Simpson's 1/3 rule, and Simpson's 3/8 rules. Okay, now the same thing applies for all of those rules. Rather than taking an entire interval, however big or small that interval is, to increase accuracy, you can artificially divide that interval into segments and then apply each one of those formulas on each one of those segments. So you treat your segment as having lower bound, upper bound, you apply the formula, and so on and so forth. And then it becomes just a repetitive thing. Okay, so now we're going to switch back to Zoom and talk about this a little bit before we wrap up. Which of these three rules, okay, so the trapezoid rule is also one of Simpson's rules. Which one of these three rules is easily applicable to discrete data? For continuous data, for continuous functions, none of those are a big deal. But for discrete data, which one of those is easily applied? Okay, I'll see you on Zoom. All right. Matthew, you're nodding your head in agreement, I guess, or in disagreement. Do you want to take this? You're nodding your head in agreement or disagreement. I'm not sure. Do you want to take this question? But remember for the 3/8 rule, x1 and x2 are in between x0 and x3. Okay, so let me show you the previous slide. These x1 and x2, they are in between the segment. So you need points in between. So I would stick only with the trapezoid rule because the trapezoid rule is only going to need the left point and the right point of the segment. There's no points in between. Remember, for the 1/3 and the 3/8 rules, we had to divide the segment into equally spaced points. For discrete data, who knows what that's going to mean, right? If it's equally spaced, you're going to have to skip every 2 points or every 3 points, which is still complicated and annoying, okay? But the trapezoid rule is the one that is easily applicable to discrete data, okay? All right, I will see you on the other side. Okay, so like we just said, the trapezoidal rule is the easiest to apply to discrete data because all you need to know is the bounds of the segment for your discrete data. You don't need any points in between, and it's a pretty accurate rule. So that's what numpy.trapz does for you. Okay, my next activity was going to be to apply a Python routine to apply the trapezoidal rule, develop a Python routine that does the trapezoidal rule for a continuous function. So we will do that, and then we'll finish up the lecture. And on Thursday we'll continue with there's just a couple more slides for in this lecture. So I was hoping that I can finish all of it today, but this going back and forth between Zoom and YouTube just sucks up 10, 20 seconds every time. So we'll just finish up with this activity, wrap up the lecture today, and then we will continue on Thursday. Okay? All right. Okay, so the question here was that I want you to apply the trapezoidal rule I want you to write a routine that implements the trapezoidal rule. So now you can focus on your Zoom screen. That implements the trapezoidal rule to integrate this should be coding activity 4 over here. Yeah. Develop a Python routine that computes the integral of a function using the trapezoidal rule for an arbitrary number of segments, and then use it to calculate this integral. So activity 4 in your Jupyter notebook, I just declared a function called trap rule f. Just call it trap rule f. And it takes a function name, a lower bound, upper bound, and a number of segments. All right. So if you've been following up with me, this just replicates whatever we were doing before. So let's see. Do we have any takers for these question marks? For the length space, we want to go from A to B. How many points? For n segments, we need n plus 1 points, correct? N plus 1 points, that gives us n segments. And then we declare our, I called it sum here, I'm going to call it result. It's result, then result. Okay. We're going to declare our result to be 0, and then we're going to loop over all of those segments. Okay. We're going to go from 0 to n. And then for each one of those segments, A, the lower bound of the segment is xi, and B is xi plus 1. And then simply you implement the Simpson's rule, which is B minus A over 2, that's 0.5 B minus A, times f of A plus f of B. All right, and now we were asked to do the function 0 to 1, 1 plus 0.5 sine squared 1.75 pi x dx. Yeah, I don't know what I have over here. Those were leftovers from last year. Okay, neglect these cells. Let's just simply call on trap rule f on my function from 0 to 1. Let's do 100 points. So that gives you 1.2727. Now compare that to integrate dot quad. My f from 0 to 1 was 1.2727. Okay, that's pretty cool. Remember, for continuous functions, you have to use numpy.quad. For discrete data, you have to use scipy.integrate.quad. For discrete data, you use numpy.trapz. Okay. These were leftover cells from last year. Don't worry about them. They were trying to just calculate the error between the two. So if we do 200 segments, again, it doesn't change much. It's a pretty good, accurate solution. Okay. We still have one coding activity and a couple of slides. I don't want to rush through those. I'll cover those next week if that's okay with you. And I'll let you ask any questions now if you have any questions. Let me see. I'm going to put this over here. All right. All right. So I think Porter had a tip for us, wisdom thing, right? All right. You want to go ahead? But you close the lid first. That's a great suggestion. Using physics applies catch-up. Yeah, catch-up. That's the. I mean, it's more viscous, but still, spinning it, you're gonna. Yeah. Hey, that's a great tip. Thank you, Porter. All right. Who's gonna volunteer for next Thursday? Wisdom, life hack. Hey, we gotta. Okay, I want someone to document all of those life hacks. Okay, who is gonna volunteer to document the life hacks? Everyone is smiling, but no one is volunteering. Come on. All right, Sammy, just create a Google Doc or something. Just start documenting them, and then by the end of the semester, we'll share them with everyone. So we've had three tips so far. Who's gonna do our Thursday hack? Life hack. Come on. Any volunteers? All right, Sarah. Okay, great. Okay. If nothing else, I will let you go. I'm gonna stick around for a few minutes if you want to talk.